Hi, my name is Bryanna Pilkington, and I received the NSERC USRA Award this summer to work in Dr. Pascale Biron's River Management Lab in the Department of Geography, Planning, and Environment. I think that my research experience this summer was perhaps a little bit different compared to most of the students working under USRAs, in that I did not focus on one specific project or research question, and instead I assisted on a few different graduate students' projects in the research lab. I have come to learn, however, that these projects are certainly not unrelated, and highlighting these links and why it is important to do so is what I hope to convey in this video. The first project I worked on was a global database of salmonid fish abundance. In short, the database will represent a compilation of data from the scientific literature and has the purpose of establishing a relationship between salmonid abundance and hydrogeomorphological stream characteristics. In other words, which streams across the world have the best or the healthiest salmonid fish populations, and is there a correlation with specific stream characteristics? For example, natural and unaltered streams typically have what we call pool-riffle complexes. This is probably something that you have seen if you have ever seen a flowing river in real life. Visually, riffles can be characterized by a disturbed water surface or what we know as rapids. The riffle sections of rivers have higher flow velocities and are generally shallower and wider. Pools, on the other hand, are characterized by calm water surfaces. This is because the water here flows at slower velocities. Pools are also deeper than the riffle sections of rivers. This series of pool and riffle in a stream is extremely important for fish populations such as salmonids. They use the coarser bed sediment found in riffles for spawning and the calmer waters of pools for feeding and resting. But when streams are altered by humans, the natural heterogeneity is also altered, and this can affect the organisms living in the stream. Which brings me to the second project I got to assist on this summer. The morphological characteristics of natural streams, such as these pool-riffle complexes that we just spoke of, can actually be assessed by something called the Morphological Quality Index, or the MQI. This index was developed by a group of Italian researchers, the result of which was an index that uses a series of characterizing metrics to assess the health of streams in terms of geomorphological processes. Let's make this more clear and go through a few examples of the metrics used in the MQI. As we discussed before, natural heterogeneity, or a varied stream environment, is indicative of healthy stream processes. Often in an agricultural setting, rivers have been dredged and straightened from their naturally meandering patterns, and this creates a more uniform and homogeneous stream environment. River straightening often causes intense river incision, as seen here, which inhibits the ability of the stream to erode laterally and return to its natural meandering or sinuous state. Straightening can affect the water velocity, the formation of pool-riffle complexes, increase risk of bank failure, among other things, and ultimately be detrimental to the organisms living within or near the stream. Thus, an agricultural stream that is straightened and incised to the extent that you see on the screen would score poorly for the functional metric called presence of a potentially erodible corridor, which assesses the stream's ability to erode laterally or side to side, which is in fact inhibited by this deep vertical incision, and it would also score poorly for the artificiality metric, artificial changes to the river course, which looks at historical changes, so if it has in fact been straightened, and scores based on the prominence of these changes. Other MQI metrics include assessing the presence of large woody debris, so trees or wood that have fallen into the stream, which increases the stream's heterogeneity and available habitat for fish, and also the presence of riparian vegetation or vegetation on the stream banks, which provides shade to streams and bank support. The scores for each individual metric are then mathematically manipulated to give a resulting number that is used to quantify the health of the stream, and this is the MQI. This number is then associated with a classification category ranging from very good to very poor. MSc student Tania Couture and I visited sites across Montérégie this summer and evaluated the MQI for streams where the surrounding land use is mostly agricultural. Tania will later compare the MQI results that were obtained this summer with fish population data. Overall, the goal is to see if streams that scored lower in terms of morphological health also score lower in terms of biological health or biological integrity of fish. But it's not just river straightening resulting from dredging and other agricultural practices that affect stream biota. There are bank stabilization initiatives that involve dumping tons upon tons of large rocks, called Riprap, in the stream beds and along their banks, essentially eradicating the water that previously flowed in the stream. This is the third project I got to learn about this summer. See, much of Quebec's soil type is clay-based, inherited from thousands of years of glaciation. Specifically, we have a lot of what are called quick clays. Quick clays can be especially precarious in areas with lots of hills and steep slopes. Let's say this house is in Quebec, built upon a quick clay soil type. The family decides that they would like to put in a swimming pool. This adds weight to the steep hill slope. Then, the area gets a heavy rainfall. The added weight in addition to the rain essentially causes the pressure between each clay particle to weaken. Eventually, the quick clay liquefies and gives way, leading to a landslide with devastating consequences. In order to prevent this from happening, engineers have applied this principle of counterweight, in that if a lot of weight is added to the base of a steep slope, it creates a sort of equilibrium that inhibits the top of the hill slope from sliding down the slope, which is where the riprap comes in. However, this is not the solution we should be applying to these cases. This summer, I visited multiple streams where this bank stabilization technique had been applied. The results have been catastrophic. This map shows, in yellow, the portion of the streams that have been riprapped. These streams are located in Blainville and the town of Lorraine, just north of the island of Montreal. The contrast between the stabilized and unstabilized portions of the stream, especially at the Blainville site, are shocking. Watch on the screen and note the differences as we move from the natural section with all of its healthy heterogeneity, large woody debris, etc., towards the massively stabilized section that doesn't even have water. Considering that there is no water, this undoubtedly has an effect on aquatic life. These projects are often done in two phases, as depicted by this diagram. Unfortunately, these drone images represent only phase 1, meaning that another meter of riprap is to be dumped on top of this already dry stream. Putting riprap on a stream is not only ecologically damaging, but is also extremely expensive, all paid by our tax dollars, of course. Better solutions have been applied, for example, this bioengineering initiative that used interlocking wood to stabilize the banks instead of massive rock dumps. Better solutions such as this one need to start becoming the norm, or we'll be in serious trouble in terms of the health of Quebec rivers and streams. Studying these biotic and abiotic processes are extremely important for the health of the stream itself, as well as the organisms living within them. And while science here is extremely important, many of these problems have a significant social component as well. So many environmental issues today are complex and linked, and most importantly, interdisciplinary. Solving them requires an understanding not only from scientists in the field, but an understanding and inclusion of all stakeholders.